So the divergence theorem, essentially, it's to calculate the flux in space. Didn't we do that before? Flux integrals? Yep. But you're gonna love this one. You'll see why. Well, number one, girl, remember how you love Green's theorem because that simplified the line integral, some of them, just finding the area of a regular geometric shape. Something similar here, something similar, but it's, well, you'll see. Okay, you'll see. I mean, you'll see the power of divergences here, the divergence theorem. Again, first of all, let's recall what is the divergence. Again, the divergence, it's a vector operation that acts on a vector field, and the result is what? Was that a vector or a scalar? Okay, let's review all of them. Let's review all of them. Forgot something I had in mind for you. Anyway, I think we can do that tomorrow. Okay. Okay. The gradient. What does the gradient act on? Does the gradient act on a scalar or on a vector?
A vector?
Or acts on... Okay, number one, acts on blank. What's the blank there? So we take the gradient of what? The gradient of a vector or the gradient of a scalar? Of a scalar. What does that produce? Another scalar or a vector? A vector, okay? So it produces a vector. Okay, what about the curl? Does the curl act on a vector or on a scalar? No, a scalar. Well, then there's the other one, right? A vector, of course. I mean, all right. And produces what? A vector or a scalar? No, not a scalar then. What was the other one, right? The vector. So a vector and on a vector. And the divergence acts on the same vector field to produce a scalar. And so while the curl describes the rotation about the different axes, that's what each component of the curl represents. The rotation about the x-axis, the rotation about the y-axis, the rotation about the z-axis. The divergence produces a scalar, which is a rate of change that describes either expansion or contraction, or at that point we say that we have a source if it's positive, or a sink if it's negative, or source free if zero, or the fluid is incompressible at that point. So source if the divergence of F is greater than 0, and sink if the divergence of F is less than 0. However, it would be incompressible, that is source free, if the divergence div F equals to 0. Okay. So again, both Stokes' theorem and divergence theorem is really Green's theorem. Both versions of Green's theorem, one for each, but in space. Okay. So again, the second version, the flux version of Green, or the flux form of Green's theorem, which we have over here. That's no longer FDR, that's M dotted with NDS. That's because we're looking at the projections of the forces going in the direction of the normal direction along the parameterized curve. And in this case, rather than finding partial n with respect x minus n with respect y, that's this time n with respect x plus n with respect y. What is this? The 2D, the two-dimensional divergence. All right? So, here it is. This is the flux form. Recall. Again, we're looking at all all these components, are all these macro components of this of the force field going outside of R, not in the direction of motion of the particle along Z. But well, what are we going to do this on? Well, did you see that surface? So we're going to do that in space. That's all we're going to do. Put our 3D glasses on and find divergences in space. Or, essentially take Green's theorem, a flux form, into space. Okay? That's it. That's all it is. Alright. So, let's have a look at the theorem. Let D be a solid region bounded by a closed surface. Closed surfaces only. We'll see why. Closed surface as oriented by a unit normal vector directed outward. Again, recall that surfaces that are closed have normal vectors that are directed outward from the solidity. And of course, what do we need for the flux to occur? We need a driving force. Otherwise, it's not going to happen by itself. Right? It's not going to happen by itself. So we need a force field. So essentially, we are going to turn, well, notice the double integral. We're going to turn this surface integral into a triple integral. Okay. Let's have a look at the first example. Determine the total outward flux of this driving force, where S is the surface bounded by that given plane and the coordinate planes. Notice in this case, the coordinate planes are going to close this surface right here. Okay, so number one, let's graph the plane. Let's graph the plane. That'll be okay, intercept. So the x-intercept, make this to equal 0. 12 divided by 3, that equals to 1, 2, 3, and 4. All right? The y-intercept, make x and z equal to 0. 12 over 2, that equals to 6. 1, 2, 3, 5, 6. Okay? Get the z-intercept, make x and y equals to 0. 12 over 2, that's another 6. 1, 2, 3, 4, 5, 6. All right, let's graph the plane. Let's graph the plane this way, okay? And of course, notice the additional information about the what's that? The coordinate planes. The coordinate planes, which are the bottom, that's the xy plane, which is z equals to 0. The xz plane, that is y equals to 0, and that wall in the back, the yz plane, which is x equals to 0. Alright? Alright. What else do we need? Okay, so they're asking us to find the total outward flux. Okay. Let's have a look at the projection. Let's have a look at the projection onto the xy plane. Okay. That is. So that's a y, that's x, that's a z. So that's 6, that's 3. All right. Oh, no, not 3, that's 4. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So the diagonal line connecting these intercepts is going to look like this. And it's going to give us the following region of integration, which is two-dimensional, by the way. Also, let's recall how would we calculate the flux outward on a surface. However, okay, let's, number one, let's set up this problem using 17.6 techniques, what we wrapped up this morning. Okay, so do you guys agree that we would need to find the flux? The flux across this plane right here. Also, the flux across the plane at the bottom. All right? Also, the flux across the YZ plane, this wall, and also the flux across the XZ plane. All right? Okay. That means we would need 4 separate flux integrals. That means 1, the flux across, so the flux across the XY plane. Oh wait, flux across, not the XY plane. Let me do flux across the plane 3x plus 2y plus 2z equals to 12. Number 2, that'll be the flux across XY plane. That is the floor z equals 0. What else would we need to do to find the total flux? 2 more. Number 3, the flux across the YZ plane, which is x equals to 0, the wall x equals to 0. And number 4, the flux across the XZ plane, which is y equals to 0. Think about this. Do you really want to do that? Do you really want to set up 4 double integrals to find the flux across each of the screens of those planes? I mean, you really want to do that? You don't want to do that, right? Remember how we started the hard way, evaluating line integrals, parameterizing every C1, C2 on a triangle, right? It wasn't the craziest problem in the world, but it was not the most efficient way. We can still do one of those. I mean, for the line integral. So what I want you to see is the comparison. I mean, the pattern here, it's pretty much the same when trying to find the total flux. So back then we found the total work by the force into moving in the particle along C equals C1, C2, C3, or as many C's as you have. Here, we're trying to find the flux, the total flux, but evaluating, I mean, even setting up every single integral. No, I don't want to do this. So that's why we're going to use the divergence theorem. However, for that, I'm going to leave you with a cliffhanger. We're going to do that tomorrow morning because we're not going to have enough time. I don't want to rush through the divergence theorem. So we'll start fresh from here. I'm going to essentially review what we did today.